our Sun, an incandescent sphere of incandescent plasma, a furnace of unimaginable power. It is the star that cradles our solar system, the eternal beacon around which Earth and its sister planets orbit. From our vantage point, it seems constant and unchanging, the same golden disk that has watched over life for billions of years. Yet, this apparent constancy is an illusion. Beneath the calm glow of daylight lies a volatile, seething powerhouse. The Sun's surface is a churning, boiling sea of electrically charged gases, threaded with magnetic fields so intense they shape its every movement. These magnetic forces twist and writhe, sometimes violently, unleashing spectacular phenomena that ripple across the solar system. Among the most dramatic of these are coronal mass ejections, immense expulsions of plasma and magnetic field that erupt from the Sun's outer atmosphere and shoot out into space. When these colossal storms strike Earth, they have the power to disrupt technology, light up the sky with dazzling auroras, and remind us of the fragile connection between our planet and its star. Today, we embark on a journey to understand the origins of these solar storms, their passage through space, and their profound impact on our modern world. The Sun is not simply a ball of fire. It is a living, dynamic star, a vast sphere of plasma, where temperatures soar to millions of degrees. At its core, nuclear fusion converts hydrogen into helium, releasing prodigious amounts of energy. This energy flows outward, making its way through the Sun's layers in a complex ballet of physics. In the convection zone beneath the surface, hot plasma rises and cooler plasma sinks, generating massive currents that churn and swirl. These currents are responsible for creating the Sun's magnetic field, a complex, tangled web of invisible forces stretching across millions of kilometers. The Sun rotates differentially, meaning its equator spins faster than its poles. This uneven rotation stretches and twists magnetic field lines into coils and loops. Some of these magnetic loops break through the surface, creating sunspots, dark, cooler regions visible even from Earth. High above the surface, these magnetic loops trap plasma, glowing brilliantly in the corona, the Sun's outer atmosphere, which mysteriously burns hotter than the surface below. These prominences can rise tens of thousands of kilometers into space, arching like fiery bridges. But these magnetic loops are under constant stress. As they twist and knot, the magnetic tension builds, until suddenly, the field lines break and reconnect in an explosive event known as magnetic reconnection. This sudden release of energy is the spark that launches a coronal mass ejection, sending charged plasma and magnetic fields hurtling into space at incredible speeds. Coronal mass ejections are the solar system's titanic storms. Each CME can carry up to 1 billion tons of plasma, electrified gas heated to millions of degrees. Hurtling through space at speeds up to 3,000 kilometers per second. To visualize this, imagine an invisible tsunami of charged particles and magnetic fields rushing outward from the Sun, expanding as it travels. These plasma clouds can grow to be larger than Earth, engulfing everything in their path. Unlike the constant, gentle solar wind, a steady breeze of particles flowing from the Sun, CMEs are violent and episodic, explosive bursts of energy. They are often associated with solar flares, intense flashes of radiation, but it is the CME's mass and magnetic complexity that makes them especially dangerous when they reach planetary environments. Embedded within each CME is a twisted magnetic field, sometimes oriented in a way that can connect with Earth's magnetosphere, triggering powerful geomagnetic storms. Scientists measure and classify CMEs based on their speed, density, and magnetic structure. Some travel relatively slowly, posing minimal threat. Others barrel toward Earth with such force that they can compress the planet's magnetic shield, shaking the space environment around us like a cosmic earthquake. The physical mechanisms that launch CMEs are still the subject of active research, but all agree on their fundamental origin. The sun's magnetic field lines, twisted and tangled until they suddenly snap, releasing pent-up energy in a spectacular outburst. Earth exists within a delicate magnetic cocoon known as the magnetosphere. Generated by the flow of molten iron in the planet's core, this magnetic field extends tens of thousands of kilometers into space, forming a protective shield against the constant solar wind. The magnetosphere deflects most charged particles, channeling them toward the polar regions, where they interact with the atmosphere to create shimmering auroras, the ethereal northern and southern lights that have inspired wonder for millennia. However, when a coronal mass ejection arrives, this shield is put to a severe test. The immense pressure of a CME compresses Earth's magnetic field on the sun-facing side and stretches it into a long tail on the night side. This sudden energy injection destabilizes the magnetosphere, causing geomagnetic storms. These storms inject currents into the ionosphere and even into the Earth's crust, inducing geomagnetically induced currents that can disrupt electrical grids and pipelines. In 1859, the largest recorded geomagnetic storm, the Carrington event, caused telegraph systems to spark and fail worldwide. If such an event struck today, it could disrupt satellites, GPS, power grids, and communication networks, an infrastructure nightmare in our technology-dependent society. Scientists continue to study how CMEs interact with the magnetosphere to improve predictions and mitigation strategies, striving to protect humanity's technological backbone from these cosmic tempests. In recent decades, humanity has learned to monitor and forecast space weather with increasing precision. A fleet of spacecraft orbits the Sun and Earth, providing continuous data on solar activity. NASA's Solar Dynamics Observatory captures high-resolution images of the Sun's surface and corona, revealing the complex magnetic dance that precedes eruptions. The Solar and Heliospheric Observatory, SOHO, has provided invaluable insights since the mid-1990s, while the twin stereo spacecraft offer stereoscopic views, allowing us to track CME's trajectories through space. In a historic leap, NASA's Parker Solar Probe has ventured closer to the Sun than any spacecraft before, sampling particles and magnetic fields within the Sun's corona itself. Its data sheds light on the origins of solar wind and the triggers of CMEs. Meanwhile, ESA's Solar Orbiter mission explores the Sun's poles, regions difficult to observe from Earth, unlocking new perspectives on the solar magnetic field. With these tools, scientists can often detect a CME minutes to hours after it erupts and track its progress toward Earth, providing vital early warnings. The Sun is both creator and destroyer, an eternal engine of life and a source of cosmic tempests. Coronal mass ejections remind us that our planet is not isolated but connected intimately to the rhythms of our star. They challenge us to understand, prepare, and adapt in a world increasingly dependent on fragile technologies. As our knowledge grows, so does our ability to live safely beneath the Sun's majestic but sometimes violent light. We are beginning to read the Sun's magnetic language, predicting its moods and guarding against its storms. The dance of Earth and Sun is eternal, a story of light, energy, and cosmic power. And as we gaze upward, we are reminded that the star that made us can still surprise us with bursts of fire.